Good morning, class. Today we'll be talking about Newton's first law of motion. In this video, there will be many demonstrations that are entertaining and easy to understand, so you can have a better feel about Newton's first law. I hope you enjoy the video.
Newton's first law of motion states, if a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed unless it is acted upon by an imbalanced force. What this means is that if an object is moving constantly in a straight line, it will remain moving at the same speed unless an outside force acts upon it and forces a change to that object's trajectory and speed. Let's say, for an example, that you're in a car going at 25 miles per hour. Then suddenly you have to brake because of a speed bump. The motion you feel when you are thrusted forward is a change in speed caused by an outside force.
What is inertia? Inertia is the tendency of an object to resist being moved. It's easier if we just show you in the following video. In this demonstration, we have an object which is being moved by an external force. As you can see, the object is in rest and is being moved by an external force. In this example, inertia is the resistance that the object is producing. Now, if the object was bigger and heavier, you could see that with the same amount of external force that is being applied in this demonstration, it would make the object move slower since it would have more resistance. Now, let's see it from another angle. Let's say that you're braking your car. The resistance that you feel when the car is stopping is inertia. Inertia was the reason seatbelts were put into cars, so when the car was braking, the inertia that was caused by the deceleration would not throw us off our seats.
Net force is the sum of forces acting on a particle or body. The net force is a single force that replaces the effect of the original forces on the particle's motion. Let's use a car to demonstrate how it works. In this clip, a car has gravity, which is an unbalanced force that is making the car move forward. We can say that there is a net force here because the forward vector is higher than the backward vector. The sum of these vectors is not equal to 0, so we can say that it has a forward net force. But if the ground was flat and there weren't any other unbalanced forces such as wind or a person pushing the car, we could say that there isn't any net force. Equilibrium is the state in which the net force in an object is 0. Here we could say that since the sum of all vectors is equal to 0, the airplane is in equilibrium. Another way to look at this is when a car is accelerating. In this clip, you can see the car is in a flat area and it can accelerate and drive easily. But what if the car was going uphill? It would become a bit difficult to accelerate but not impossible. Unless the car is not in equilibrium, then it would become a bit difficult to drive it and maybe even dangerous. What if the car was towing a heavy boat and the road it was climbing was too steep? Then maybe the car would not have enough horsepower to climb the road. This is why equilibrium is also very important.
How are inertia, net force, and equilibrium related? Since inertia is a tendency of an object to resist being moved, and net force is a vector sum of forces acting upon a particle or body, you can say it's related because inertia is how much an object resists being moved. The net force is the resulting amount of movement caused by all the forces being applied to that object. But if all the forces that are being acted upon the object cancel each other out, the result will be 0. We can say the object is in equilibrium and has 0 net force. Let's put an example for each one. First, we can see that when the ball was in the floor, it was in equilibrium since there was no forces being acted upon it. Secondly, we can see the inertia because of the resistance of the ball, since its state of rest was interrupted by an unbalanced force, which in this case was the person picking it up. Lastly, in this clip, we can see the net force being acted upon when the ball was hit, causing its forward vector and upward to surpass the backward and downwards vectors. And of course, we shouldn't forget that since gravity and friction are still at work, eventually the ball will come to a complete stop. But if there wasn't any friction, the ball could continue going in a forward motion forever.